Hi everyone, in this video we are going to look at an important result called the divergence theorem. So let's go back to the vector version of the Green's theorem, which is given by f dot and cap is the double integral of the divergence of the vector field f. And we can extend this to R3, which is when it is called a divergence theorem. And basically it says that the surface integral of f dot and cap is the same as the triple integral of the divergence of the vector field found over the region E. The theorem states that let E be a simple solid region and S be the boundary surface of E, given with a positive, which is outward orientation, so the normal vector is pointing outward. Let F be a vector field whose component functions have continuous partial derivatives on an open region that contains E. Then the surface integral f ds is the same as the triple integral of the divergence of f. Let's apply this to a problem which says find the flux of the vector field zyx over the unit sphere x squared plus y squared plus z squared equals 1. We did this earlier in the video, the same example where we learned about flux and how flux is just a surface integral, right? Here we will see that applying the divergence theorem makes everything much easier. So we are given f is zyx. So all we're going to do is find the divergence of f, which is partial derivatives. So del z del x of z, del y of y, and del z of x. Two of them are 0, the middle one is 1, so this comes out to be 1. So what does the result say? Well, flux is surface integral of a vector field, so that's that. Then divergence theorem says this is the triple integral of the divergence, but that comes out to 1. And what do we know from triple integral is, if I'm taking the triple integral over a region, and the function itself is constant, it means it's a uniform density scenario, then this is just the volume of B. But what is this? What is this B? B is a sphere. Volume of a sphere is 4/3 pi r cubed unit sphere, so we get 4 pi over 3, which if you go back in your notes, we'll find it's the same result that we obtained when we learned about flux for the first time. However, at that point, there was much more involved calculation as opposed to now, where, it's just volume of sphere. So that's one application. Let's look at a second example. Evaluate the flux again. In this case, it's not mentioned as flux, but whenever you have surface integral of a vector function, it is flux, where the vector field is xy, this stuff, and sine xy. So once again, here the idea is, well, you have e raised to some stuff, which is not simple. So it means it's basically hinting you to maybe find the divergence and hope that that will be something easier. Then you have the region. The S is the region bounded by a parabolic cylinder z equals 1 minus x squared, the plane, and these three planes. So the region itself is also not as simple like we had before, which was a sphere. So what is this region? So you have a parabolic cylinder, right? So that extends down, but it has been cut along its, it would usually just keep going like that, but it has been cut at an awkward angle so that, we're only dealing with this part and the surface that was cut. So we have something like that. So this is a plane y plus z equals 2 that is cutting through it. Y, x, z, So what is this point here? Because this is cut by this plane, this point is going to be 0, 2, 0. This surface is the whole z equals 1 minus x squared. That gives it the parabolic shape. This is 0, 0, 1, and this here is 1, 0, 0. All right, what's my field? My field, somewhat complicated, but we're hoping that when we take the divergence, things simmer down. Divergence of f, that's going to be a vector, so del x, xy, del y of this complicated stuff, and del z of sine xy. 0, no z term, 2y, y. So good news, all of this gets reduced to just a singular y term, which is 3y. So my flux, or the surface integral, is now the triple integral of the divergence of f. So it's a triple integral in the region E of 3y dv. Now, all we gotta do is figure out the limit stuff here. So for figuring out the limit stuff, we already have all the equations, so it's pretty straightforward. Pull out the 3 outside, so we have y. Let's go with dy first. Where does y go from? Y goes from, if you look on the y direction, it starts at 0, and it ends over here, where y is 2 minus c. So you get 2 minus c. Then let's go to z. Z also starts from 0, and z ends at this dome, which is given by 1 minus x squared. And then we have x. X also starts at 0, but ends at 1. Oh, sorry, x starts at negative 1 here and ends at 1. So you have the first integral gives you 1/2 and a y squared, which makes it a 2 minus z squared dz dx, 0, 1 minus x squared, negative 1 to 1. Then this will give you a 1/3, a 2 minus z cubed, but with a negative, and a 0, 1 minus x squared, negative 1 to 1 dx. So now you have you're carrying a negative half now, negative 1 to 1. Plug in this, so 2 minus 1 minus x squared is going to be 1 plus x squared. So you have 1 plus x squared cubed minus 8 dx. That's going to be a polynomial here, so you get 1 plus x to the 6 plus 3x squared plus 3x 4 minus 8 dx. And these are all just polynomials, so x to the 6 gives you an x to the 7 over 7, negative 1 to 1. You get a 3x cubed over 3, negative 1 to 1. 3x to the 5 over 5, negative 1 to 1, and a negative 7x, negative 1 to 1. You get a 1/7. These are all odd powers, which means when you plug in 1, you get 1. When you plug in negative 1, you get negative 1. But because you're subtracting, they're just going to add up. So this will be 1 plus 1, so giving you 2, and then another 2, and then another 2, and then another 2. So you have negative half, 35. That'll be 10 plus 70 plus 6 times 7, 42, and 14 times 35, which is 20, 12, 15, 17, 19, 1, 3, 4, 490. And all of this, eventually this will be negative, which will cancel out, and it should come out to 185 over 34. So once again, this divergence theorem is a tool which helps you go from a surface integral to a triple integral, which in some case might be very simple, and you might just end up with a constant 1, which means it's simply the volume of the given region. All right, that's it for this particular video. Thanks everyone.